This is the Module 4 exam review for statistics. Problem number 1. Based on the data shown below, calculate the regression line, each value to 2 decimal places. So I'm going to need to put this data in my calculator so that I can run the regression test and get a regression line. So I'm going to put the X values in L1. I'm going to put the Y values in L2. So I'm going to share my calculator. And I have already put that information in my list. So I'm going to go Stat, Edit. And you can see in L1 and L2, I have that data. All right, so now I'm going to go run the regression on that data. So I'm going to get out of here. I'm going to go back in my Stat menu. I'm going to go over to Tests. And the menu I'm going to look for, the menu item, is the LinReg t-test. I'm going to run a linear regression t-test on that data. So hit enter, and then tell the calculator where that data is located. I put my X's in L1. I put my Y's in L2. And it doesn't matter about the rest of this. You're not going to worry about this right now. We'll talk about that when we get to the problem where we're actually finding rho. So then we're going to calculate. So the linear regression equation is y equals a plus bx. So a is the y-intercept, and they tell us that a is 16.23 to 2 decimal places. B is the slope, it's the coefficient on the x, and they tell us that B is 0.59 to do 2 decimal places. So we're going to go enter that in the field. So we got y hat is a plus bx, and they told us that a was 16.23 and b was 0.59. So we're going to put that in. 59. All right, problem number 2. You intend to conduct a goodness of fit test for a multinomial distribution with 4 categories. 4 categories. You collect data from 75 subjects. What are the degrees of freedom for the chi-square distribution for this test? Degrees of freedom for a chi-square test is the number of categories. So the number of categories minus 1. So that would be 4 minus 1, 3. Problem number 3. You are conducting a test of independence for the claim that there is an association between the row variable and the column variable. And they give us the row variables A and B and the column variables X, Y, and Z. The expected observations for this table would be, so we're going to go calculate that in our calculator here in just a second. What is the chi-square test statistics for this data? So we're going to calculate that too. So first thing that we must do is get some row totals and column totals. So I need to find the row total for A. So I'm going to add the 9, the 44, and the 18. And I'm going to write that right there. That's 71. Then I'm going to get the second row total. I'm going to get the total for row B, and that is 85. Then I'm going to get the column totals. So I'm going to add up the column X, that is 33. Column Y is 85. And column Z is 38. And then I'm going to find the total total. The total total is the total of the columns or the total of the rows. they should equal the same value, and I get 156. So I'm now going to put this table in matrix A in my calculator. And I'm going to calculate the expected values in matrix B. And to calculate the expected observations for this table, we're going to take the row total for whatever row we're in. We're going to multiply that by the column total for whatever column we're in. And we're going to divide that by the total. In this case, 156. And we're going to do that for all 6 elements in this table. And I'm going to put that in matrix B. So I'm going to share my calculator. And I'm going to go to my matrix menu. To get to my matrix menu, I do second inverse. You can see in blue right above that inverse key is matrix. And I have a whole slew of matrices in my calculator because I was using my calculator for college algebra. So I need to get rid of those. I'm going to start fresh. So I'm going to exit out second mode. That gives me the quit. And I'm going to go to my memory, which is above my plus sign. So I'm going to go second plus, and I need memory management delete because I'm going to have to delete those matrices. Number 2, and then number 5 is matrix. So go to number 5, and then I'm just going to delete all those by using the delete key on my calculator. Delete, delete, delete all those. Now, when I go back into my matrix menu, I have no matrices. So that first table, I'm going to put in matrix A. So I'm going to go to my edit menu, and I'm going to edit A. So I hit enter. Now there are 2 rows in that table and 3 columns, 2 rows A and B, and 3 columns X, Y, and Z. So this is a 2 by 3 matrix. So 2, enter, 3, enter. And when I do that, it creates the matrix for me. And now I'm just going to put the elements in this matrix by rows. So I'm going to put the A row in and then the B row. So the A row was 9, 44, and 18. And then when I hit that last element and enter it, it drops me down to the second row. The second row was 24, 41, 41, and 20. Now I'm going to do a quick check of that to make sure that I have all those elements entered correctly, and I do. So I have the first table inputted into my calculator in matrix A. Now I'm going to put the second table of the expected values of that table in my calculator. So I'm going to exit out of this matrix and then go back in the matrix menu. So second inverse, and you can see now that that matrix has been entered. I'm going to go to edit, and I'm going to edit B, number 2. Again, it's going to be a 2-row, 3-column matrix. Now, how do I calculate what each element in the expected value table is? I take the row total, I multiply it by the column total, and I divide it by the total. So the first row in that table, its sum was 71. So I take 71. The first column total was 33. So I multiply that by 33. And I divide that by the total, and that was 156. So the expected value in the first row, first column, is 15.02. And then I repeat the process for the remainder of the elements in the table. So The first row total was 71. The second column total was 85. The total was 156. So we take the row total, 71, times the column total, 85, and divide it by the total. And I get 38.686. Continuing, the row total for that first row was 71. The column total for that third column was 38, divided by the total, 156, and I get 17.295. Now I'm going to do the second row. The second row total was 85, times the first column total was 33, divided by the total, which was 156. I get 17.981. So now we're going to do the second row. Total was 85. The second column total was 85, divided by the total, which was 156. So we get 46.31. And then the row total was 85. The column total was 38, divided by the total, 156. So we get 20.71. Okay, now when I inputted this into my lab math, the 17.295, it counted it incorrect when I rounded that up to 17.3. So be aware, I will check that to make sure that my lab math is not going to count that incorrect. All right, so let's stop share, go back to my paper. So now I'm going to just write those or type those in to the fields, and it does tell me to 2 decimal places. So I got 15.02 here, 38.69 here, 17.29 here, and 17.98, 46.31, and 20.71. And again, it counted the 17.3 incorrect when I put that in, so I changed it to 0.29. It should be 0.3. All right, now I need to calculate the chi-squared statistic. The easiest way to do that is to use the chi-squared test on your calculator. So I'm going to share my calculator again. And I'm going to go run a chi-squared test. So I need to exit out of my matrix menu, get back to the home screen. We're going to go stat test, and I'm going to find the chi-squared test. So I want C, the chi-squared test. And I'll know that that is the correct test because it's going to ask me for matrices. It's going to ask me where I put the table of observed values. In that first table, I put that in matrix A. So I go second matrix number 1. So now the observed values, what we observed, was in that first matrix. The second table that we created that in matrix B. So I go second matrix 2B. All right, and then I calculate. And it will calculate the chi-squared statistic for me. So the chi-squared statistic is that top number, 5.82. And then in another problem, we'll talk about the p-value. It doesn't require that you put the p-value in this problem, just the chi-squared statistic. All right, problem 4, choose the most appropriate completion of the sentence. In order to indicate a strong correlation between variables, the correlation coefficient will be, well, it has to be near -1 or +1. Correlation varies from -1 to +1. The stronger the correlation, the closer you are to either -1 or +1. Oh, another matrix problem, another table problem. You are interested in investigating whether gender and major are associated at your college. The table below shows the results of a survey. So we have in the rows, men and women, and across the columns, we have various majors. We have math science majors, arts and humanities, business, econ, and then other majors. So the first thing I need to do is again get the row and column totals. So that first row, which represents men in the survey, I got 311. In the second row, 54 women. And then we need to sum up each major. So math and science, I got 206. For arts and humanities, I got 204. For business econ, I got 177. And other, I got 78. So the total, either sum the columns or sum the rows, you should get the exact same value. I got 665. All right, so what are we doing here? We're doing a test of independence. Is gender independent from your major? So we're doing a test of independence. Is gender independent of your major, or is major independent of gender? So what are we doing here? College major and gender are independent. They don't depend on each other. College major and gender are dependent. So our null hypothesis is that they're independent. They are not related to each other whatsoever. The alternative hypothesis is the opposite, that they actually are dependent on each other. Okay, so now we need to go put these two tables in our calculator, and we need to calculate the chi-squared test statistic, the p-value, and then compare the p-value to alpha. So I'm going to share my calculator. And we're going to go through the same process we went before. We're going to put what we observed in a matrix, and then we're going to put what we expect in another matrix. So I'm going to go second matrix, there we go. I'm going to go to edit, and I'm going to put this in C. I'm going to leave A and B alone until I finish my exam, because I might want to go back and check those. So I'm going to do this in 3. Okay, so we had 2 genders, male and female, male. So we have 2 rows. And then how many majors did we have? We have math, science, arts, humanities, business, econ, and others. So we have 4. So we have 4 columns. And now I'm just going to put that information in. We had 87 male math science majors, etc. So we had 93 arts and humanities majors who are men. We had 86 business and econ majors that were men. And then we had 45. They had some other major. Now, of the women, we had 119 in math and science. We had 111 in arts and humanities, 91 in business econ, and 33 in some other major. Okay, so that matrix is done. I'm going to exit out of it. I'm going to make sure that I inputted everything correctly. I did not. I see a mistake. So I'm going to go over to that element. That should be 111. So this is why I always check. That's 91, that's 33. I always check what I've inputted to make sure I did it correctly. Okay, now I'm going to exit. And I'm going to go back in the matrix menu, and I'm going to put in what I would expect the values to be. And I'm going to put that in D. So I'm going to edit number 4. And again, it's 2 rows and 4 columns. And we are going to calculate those. All right, so that first row, first column, we're going to take the row total, which was 311. We're going to multiply that by the column total, which was 206. And we're going to divide that by the total, which was 665. So row total times column total divided by the total number in the table. And I understand these are going to be decimals, but I don't care. We would know that it wouldn't really be 96.34 people, but that's all right. Okay, so we're going to do the next one. The row total was 311. The column total for arts and humanities was 204. And we're going to divide that by the total, which was 665. The next one, we had 311, number of men, times business econ, there was 177 of those, and divided by the total. And then the other 311 times 78 divided by 665. All right, the next row, females, we had a row total of 354, a column total for math and science of 206, divided by the total, 665. The next column, we had a row total of 354, a column total of 204, and divided by the total, which was 665. The next one, we had a row total of 354, a column total of 177, divided by that total, 665. And the last one, we had a row total of 354 times a column total of 78 divided by 665. And I was kind of spacing out a little bit on this one here. So I'm going to go check that. So at 354 times 204 divided by 665. I think it was okay. All right. So now we're going to exit out of here. So let's go back and look here in my matrix menu. I put the observed values in C, and I put what I would expect to see in D. So that's what I'm going to use when I run the test. I'm going to get out of here, quit, go into my statistics menu, go find the chi-squared test. And I know it's the correct test because it asks me for matrices. And I put what we observed from the survey, I put that in C. So we go second matrix, number 3. I put what I expected that I calculated, I put that in D, number 4. And then we calculate. So our chi-squared statistic is 5.790, and the p-value is 0.1223 to 4 decimal places. So let's go put that in. So the chi-squared statistic that I calculated, it tells me to do this to 3 decimal places. So that was 5.790, and the p-value was 0.1223 to 4 decimal places. Okay, alpha is 0.05, so 0.1223 is way bigger than 0.05. So if the p is high, the null must fly, so we fail to reject. So that is greater than or equal to. I think there's actually, it's in words, greater than or equal to. Greater than or equal to, and we're going to fail to reject the null. If the p is high, we can't reject the null hypothesis. So what's our conclusion? Well, if we're failing to reject the null, then we're not agreeing that the alternative is true. So there's not sufficient evidence to conclude that the alternative hypothesis is true. So of the choices here, we have the last one. There's insufficient evidence to conclude that college major and gender are dependent. So we don't reject the null. So there's not sufficient data to support the fact that these two things are dependent on each other. Insufficient evidence to conclude that college major and gender are dependent. Okay, problem 6. Another one. A researcher is interested in investigating whether living situation and pet ownership are dependent. The table below shows the results of a survey. So again, I need to add the rows and the columns. So this is 273, 279, 155, and 163. And then we got 296 for that first column, 303 for the second column, and 271. So the total is 870. So total that all the columns, or total the the 4 rows or the 3 columns, and you should get 870. So this is a test of independence. If we're given a contingency table, we will be testing independence. So what are we testing? We're testing whether or not living situation and pet ownership are dependent or not. So we're testing whether pet ownership and living situation are independent, or is pet ownership and living situation dependent? Which one is it? All right, so we're going to go put this in our calculators. I'm going to put the observed, this table, in E. And I'm going to put what we calculate for the expected in F. Because I don't really want to delete a matrix until I'm done. All right, so go to our matrix menu. And I'm going to edit. I'm going to edit 5. Okay, so that data table had 4 rows: dog, cat, various, none. So 4 rows. And it had 3 columns: single, family, couple. Okay, I'm going to put that information in. Well, hopefully I'm going to put it in. There we go. Okay, I'm going to do a quick check to make sure I inputted that table correctly. The first column should be 78, 113, 44, 61. The second column should be 99, 99, 51, 54. The third column should be 96, 67, 60, 48. All right, so there are the values that I observed. Now we need to calculate what we would expect. So we're going to exit out of here, go back into our matrix menu. We're going to edit, and we're going to edit F. Again, I have 4 rows, and I have 3 columns. And now we're going to do our calculation. So we have 273, which is the row total for that first row, times the column total, which is 296. And we're going to divide that by the total, which is 870. And we're going to continue doing the rest of these elements. So we have 273 times 303 divided by 870. 273 times 271 divided by 870. Let's continue with the second row. 279 times 296 divided by 870. 279, which is the row total, times the column total, which is 303, divided by the total, 870. The next element, the row total is 279. The column total for couple was 271. We're dividing that by the total, 870. The third row total was 155 times that column total was 296 divided by the total, 870. That row total was 155. The column total for the second column was 303 divided by 870. The next one, we had a row total again of 155. The column total was 271. The total was 870. The hardest part of these problems is just entering all this information. Okay, that last row, the total was 163 times the column total, 296 divided by 870. And then that next one, the row total for that last row was 163 times the column total was 303 divided by the total, 870. And then last but not least, the row total is 163 again, times that column total was 271 divided by the 870. Okay, so we are good to go. So we're going to exit out. We finished with our matrices. Now we're going to go run the chi-squared test. So we go stat, test, find the chi-squared test, which is C. And we did that on matrices E and F. So we're going to go second, matrix E, and F, second, matrix F is number 6. And then we're going to calculate. So the chi-squared statistic that we get is 17.292, and the p-value is 0.0083. So we're going to go put those in. So they tell me to 3 decimal places, 17.292, and the p-value is 0.0083. I think they told me 4 decimal places. Okay, that p-value, what was alpha again? Let me scroll up. 0.01. So alpha is 0.01. Our p-value is 0.0083. Okay, p is less than alpha. If the p is low, the null must go. So we're going to reject the null hypothesis. So our data does support that these are independent. The data supports that the kind of pet you own depends on your living status. So we have sufficient evidence. So it's one of the last 3. So let's read. There's sufficient evidence to conclude that the distribution of pets, that's not it. There's sufficient evidence to conclude that pet ownership and living situation are dependent. I believe that is it. Let's read the last one. Sufficient evidence to conclude that pet ownership and living situation are, nope. When we rejected the null hypothesis, we reject the notion that they're independent. and we accept, and you can't see my air quotes, accept the fact that they are dependent. Our data indicates that these two things are dependent on each other. All right, very simple. The regression was run to determine if there's a relationship between the hours of TV watched per day and the number of sit-ups a person can do. I think that's funny. The results of the regression are y hat. Again, y hat is the predicted value from your data. So your calculator takes your data, it runs a linear regression on it, and it gets a predicted value, and that's what these are. Y hat is A plus BX. Y hat is A plus BX. And A is 29.794. And B, the slope, is negative 0.816. And we're going to replace the X with 11.5. So we want to know the average number of sit-ups I can do if I watch TV 11.5 hours. So we're going to find the predicted value from our regression equation. Times 11.5. So I take my handy dandy calculator out and I calculate this and I get y hat is 20.41. So my regression equation predicts that if I watch 11.5 hours of TV, I'm going to be able to do 20 sit-ups. It sets to 1 decimal place, so 20.4. Question 8. All right, so we're going to do a chi-squared goodness of fit test. You're conducting a multinomial hypothesis test for the claim that the 4 categories occur with the following frequencies. So category 8 occurs 50% of the time, category B 10%, C 10%, and D 30%. So the first thing I need to do is I need to add up how many observed frequencies I have. So I'm going to add the observed frequency column and I get 128. Then I can calculate the expected value because I expect that the category A occurs half of the time, 50% of the time. So we're going to calculate the expected. So expected, the first category, category 8, we expect it to occur 50% of the time. So we multiply our total frequency by a half and we get 64. The second category B, we expect it to occur 10% of the time. So we take 10% times the 128 and we get 12.8. We expect the category C also occurs 10% of the time. 0.1 times 128 is 12.8. And we expect that category D occurs 30% of the time. So 0.3 times 128, which is 38.4. Now, I could put this in my calculator and let my calculator calculate the squared residual for me. Just to remind you what that formula is, the squared residual. You take the observed, you subtract the expected, you take that result, you square it, and you divide by the expected. So that first, let's write that up above this so we can actually do the calculation. So the squared residual is O minus E squared divided by E. So we're going to take the observed value, 61. We're going to subtract the expected, the 64. We're going to square that and divide that by 64. So you take your handy dandy calculator out, you take 61 minus 64, that's -3, but you're squaring it, so it becomes +9. 9 divided by 64 is 0.1406. And you continue in the same way with the rest of them. You have 8 minus 12.8. 8 minus 12.8. You square that and divide it by 12.8. You take 12 minus 12.8. You square that and divide it by 12.8. You take 47, excuse me, minus 38.4. It really doesn't matter in what direction I take this difference because I want to square it and force it to be positive 38.4. So I do the rest of those calculations and I get 1.8 here, 0.05 here, and 1.926. So I add the squared residual column, and that gives me the chi-squared statistic. So if I add that column up, I get 3.917. Now I can also put this in my calculator and let my calculator calculate it for me. Now I do need to calculate the expected value before I put this in my calculator. And I'm going to put these in a list. So I think I've used L1 and L2. So I'm going to put this in L3 and L4. So I'm going to put what I observed in L3 and I'm going to put what I expect in L4. So I'm going to share my calculator. And I'm going to go Stat, Edit, and you can see that I have this data in my calculator. So the observed values is in L3, and then when I calculated for the expected value is in L4. So I'm going to get out of there. I'm going to go to my Stat menu, to my test, and I'm going to find the chi-squared goodness of fit, because what I'm trying to test is whether or not what I observe is what I expect. So I'm going to do the chi-squared goodness of fit test. Is what I see what I expect to see? So we're going to we put our observed in L3. So L3, and we put our expected in L4. And I do need to tell my calculator the degrees of freedom. I had 4 categories, A, B, C, and D were my 4 categories. So my degrees of freedom is 3, the number of categories minus 1. Calculate. And I get the same exact answer. The chi-squared statistic is 3.917. And down here, this last row, you see that? Those are your squared Pearson residuals. Those are your squared residuals. So if I use my arrows, the first one's 0.1406, which is exactly what I calculated. The next one's 1.8. That's what I calculated. 0.05. And just use your right arrow and you can just move over. And then the last one was 1.926, which is what we calculated. So your calculator can calculate the squared residuals for you. Problem 9. Same question. Now this one, what you expect is slightly different. Well, it's completely different than what you did before. You're conducting a multinomial hypothesis test for the claim that all 5 categories are equally likely to be selected. Complete the table. So I need to find the total observed frequency, and my calculator says that totals 128. If they occur with exactly the same frequency, all 5 of these categories occur with exactly the same frequency, then I'm going to take the 128, I'm going to divide that by 5, and that is going to be my expected frequency for each category. If they all occur at the same frequency, each of those need to be equal to each other, and I get 17.4. So these are all 17.4. Okay, now to calculate the squared residual, need to make some room here. So let's write this down here. 128 divided by 5 is 17.4. So we take O minus E, we square that, and we divide that by E. So that first one, we'll just do the first one, and then I'll leave you to do the rest of them. So we take 6 minus 17.4, we take that result, and we square it, and divide that by 17.4. And I get 7.469. And then I do the same for the rest. 20, it won't take me too long to write this down. 20 minus 17.4, we square that and divide it by 17.4. We take 23, we subtract 17.4, we square that, divide it by 17.4. We take 23, we subtract 17.4, we square that and divide that by 17.4. We take 15, we subtract 17.4, we square that and divide it by 17.4. So I get, for the rest of these, 0.3885, 1.8023, 1.8023, and 0.3310. Add that up, add that last column up, I get 11.793, and that is chi-squared. Problem 10. So we need to run a regression here. Listed below are paired data consisting of amounts spent on advertising in millions of dollars and the profits in millions of dollars. Determine if there's a significant linear correlation between advertising cost and profit. So that's all we're trying to determine, whether there is a correlation or there isn't. So our null hypothesis is that the population correlation is 0. There is no correlation. And then our alternative is that the population correlation is not 0. So there is a significant linear correlation between these two variables. Use a significance level of 0.1 and round all values to 4 decimal places. So I need to put this data in my calculator and then run the regression test. So I think I've used list 1 through 4, so let's use 5 and 6. I'm not real keen on deleting stuff while I'm in the middle of taking a test. Okay, so let me share my calculator. And I've already put this data in my list. This should be in L5 and L6. And it is. Let's move over there. There's an arrow over so we can see 6. Okay, so I have the data inputted. So I'm going to go run a regression on L5 and L6. I'm going to get out of here, go stat, test, and find my lin-reg t-test, which is F. And I'm going to run that linear regression t-test on, I put my data in 5, my X list, and my Y list I put in 6. Okay, now my null and alternative hypotheses were that rho was equal to 0. That was the null. And the alternative was that it was not equal to 0. So I want to make sure that's highlighted. And then let's calculate. All right, so we got all sorts of information here, but what is it is wanting? It's wanting R, and it's wanting the p-value. So the p-value is right here. It's 2.7723. See that -4 over there? Times 10 to the -4. So there are 3 zeros in front of that 2, to the left of the 2, and to the right of the decimal place. So p-value is 0.00028. So there are 3 zeros in front of that 2, but to the right of the decimal place. Now I need to arrow down to find R, and R is right here. R is -0.97 0.07. So I'm going to go put that in my OpenMeth. So R was negative 0.9707, and the p-value 0.0002. So 3 zeros and then a 2. Okay, so now I need to make a decision. And what's my decision? Well, that's a really small p-value, itty bitty. P is low, the null must go. So I'm going to reject the null hypothesis because that p-value is going to be less than alpha. That's itty bitty. So I'm going to reject the null. So there is sufficient evidence to show that there is a strong linear correlation. So which one says strong linear correlation? Is that the second one? Strong linear correlation between advertising and expense and profit. Okay, now we got a bunch of really simple ones to answer. True and false. If the slope of the regression line is positive, the correlation is also positive. That is true. The correlation has the same sign as your slope. Study was done that looked at how much red meat people consumed and how long they lived. The correlation R was found to be 0.98, and the p-value for the correlation was 0.0005. Then a person who does not eat red meat will live longer. I don't know. I don't know that I can conclude that from that. I'm thinking not. What do we got here? If the equation of the regression line for hours X spent cycling in the summer and hours Y spent working in the summer is Y hat, which is again your predicted value, is negative 0.7x plus 42. Then as the number of cycling hours increases, so X is the cycling hours, and Y is the number of hours that you work. As the number of cycling hours increases, the number of work hours tends to decrease. What makes sense? But the slope for this line is negative 0.7. And if you have a line that has a negative slope, that means it's going down. If it's going down, that means as X gets bigger, Y gets smaller. So as the number of hours that you cycle around on your bicycle increases, then obviously the number of hours you're going to work is decreasing. So according to this model, this linear regression model, that is true. Data was collected on the distance from, oh, this is just, I have to read it. The data was collected on the distance from a runner's belly buttons to the ground and the time it takes them to run 100 meters. R squared is 0.87, then 87% of runners with belly buttons far from the ground will run faster than average. I'm pretty sure I can't predict that. And then the last one. Last question. A researcher used a chi-squared test for independence where the two variables were eye color and hair color, and a p-value of 0.0001 was produced. Then the researcher can conclude at a 5% level of significance that eye color and hair color are independent. I don't think so. Alpha was 0.05. The p-value was 0.0001. Well, the p-value is less than alpha. The p is low, the null must go, so we're going to reject the null hypothesis. So we reject the fact that they are independent. The data indicates that they're actually dependent. So this is false.